Hi everyone, this is Alex Khan. Thank you for showing interest in our presentation on how D-Wave can be used to optimize the lockdown schedule of cities through COVID-19 crisis while opening up cities and the economy. Since COVID-19 started spreading from Wuhan, China across the globe, a lot of research has been done on the transmission to predict level of illness and spread. We show that a hybrid quantum approach can be used to provide an optimal lockdown schedule which continues to suppress the rate of infection while maintaining the economy. The common disease evolution model is called the SEIRD model, which represents the evolution of a transmissible illness from the susceptible S population to those who get infected I, and then finally their recovery R, using a number of partial differential equations. The number of people that get sick and how fast the disease spreads are controlled by parameters like beta, delta, and gamma. COVID-19, with its higher incubation period, where the person can be infectious and the higher mortality rate, requires an adjustment to this model. We thus adopt the SEIRD model that adds exposed and dead. This model only involves the disease within one population center. So we also add a transfer function that allows the disease to be transmitted from the infected of one region to the susceptible population of the next. We model the 5 cities in India on a graph, where the distance between the cities is the primary input to the transfer function. Larger the separation between two cities would imply smaller the impact of the infected from those cities on each other. The function can be calibrated over time to ensure it is adequately accommodating various roads and air traffic between the two cities. In our model, we assume that shutting down a city brings its GDP down to 0, and the net movement of population between cities is also 0. We do not consider the impact of age, and the parameter values are simply approximations and are not fully calibrated. The model is evolved over time in phases. We let the SEIRD disease model evolve based on its partial differential equations in each population center, picking up illness from other population centers through the transfer function. We do this for a period of 5 days. Next, we use the GDP, the number of infected in each population, and the hospital bed availability around the country as inputs to the optimization function. We optimize both classically and using D-Wave's quantum annealing hardware to determine which cities need to be placed or kept in lockdown and which should be opened up. This ends one phase, and the lockdown schedule is then maintained during the next phase. We continue these alternating disease evolution and impact optimization steps 20 times, or in 20 phases, to represent a 100-day period.
Hello everyone, myself Arindam Sadhu. As mentioned by our colleague, our problem is to kind of balance the object on two sides of a seesaw. As per Knapsack problem, here in this project, we want to minimize the weight, that is our infected population, and subject to maximize the profit, that is an effective economy, and in our case it is GDP. Hence, we can say that the Knapsack problem model and our problem is almost similar one. The quantum algorithm for Knapsack problem is formulated by Andrew Lucas, and he reported his work at the manuscript titled as Easing Formulation of Many NP Problems. The knapsack formulation is expressed in the following equation on this slide, where H suffix A states that the inequality of minimizing the weight of the knapsack, and HB or H suffix B states that to maximize the total profit of the knapsack. For our case, the objects that open cities are in the knapsack, and the object or the cities that are not included in the knapsack means the cities or the objects are in lockdown for a specified phase. Hence, open cities have a running economy. That means the cities are open and able to utilize their hospital capacity to maintain the economy. Whereas the economy for closed one is assumed to be zero. Hence, using Knapsack QUBO, we can achieve to find out the solution of our problem, that is optimized lockdown subject to maximize the GDP globally.
Let's now look at the result of our two model, D-Wave and Classical. We have printed out a scheduled lockdown calendar for 100 days over 5 interval period, where caps O denote the city is open and caps X denote the city is in lockdown. We can use this schedule to achieve our goal of decreasing the COVID-19 infected population subject to maximizing the global economy. Any city that is either open or locked down will be in that state for the interval period, that is 5 in our case. The left figure shows us the evolution of infected population over 100 days, where no lockdown is implemented throughout the time, while the right figure D-wave plot shows us the same but implementing optimal lockdown using the lockdown schedule calendar from the previous slide. Using the lockdown calendar, we have reduced the infected population for all of the cities. For Mumbai, we have reduced the infected population down to 2.2 million from 26 million. It's a huge improvement. We saw using our model we have reduced the rate of infected population over time using the lockdown schedule calendar. But what about the economic factor GDP or the death count? Well, in the left figure you can see the comparison of maintaining GDP over time for our two model, and in the right figure we can see the death count for the 5 cities. We can notice in the left figure the classical knapsack problem is maintaining the GDP or the global economic factor better than the quantum knapsack problem. While for the case of the death count, the quantum knapsack problem is maintaining the death count, that is reducing the death count in a better way. Hence, it is a nice comparison between our two model, quantum and classical knapsack problem. What about the available resource, that is COVID-19 hospital bed capacity? We can follow that without any lockdown, the lack of resource availability, that is bed capacity, is decreasing at the rate of exponential. But using our model, we have reduced the rate of decreasing the availability bed up to a great extent using our optimal lockdown schedule, especially for the case of quantum model. Yet there is a lack of necessary bed capacity. So we assume that the rest of the infected population goes in quarantine at home. So using our multi-city SEIRD model for predicting the flow of COVID-19 and obtaining a lockdown schedule using our classical and quantum optimal lockdown model, We not only decrease the rate of infected population for all of our cities over time, but also maintaining good economic factor, that is GDP. Using our experimental data, we saved about 2.5 million individuals. Hence, we successfully achieved our goal of optimal lockdown subject to maximizing global economy.
As Sahil just mentioned, with a test model of only 5 cities, we can bring the GDP up to approximately 45% in the 100 days, compared to full lockdown where it would be 0%, and also prevent over 70% of the death count if lockdown had not occurred by optimizing the lockdown schedule and using the Knapsack formulation on D-Wave. The classical method and D-Wave quantum annealing showed interesting differences because of the probabilistic nature of both models. With increasing sampling, we assume that both results would be similar. However, small variations at each phase can cause the difference in optimization at subsequent phases due to the chaotic nature of this problem. With large number of cities and the transfer rates, D-Wave would scale well with this formulation, and we can even use D-Wave hybrid sampler for more than 60 cities. We thus suggest that this model with adequate validation and medical and policy oversight can be used to predict disease transmission patterns and schedule variances to implement the best possible lockdown schedule to both stop the disease spread and sustain the global economy. We have used the Knapsack formulation to optimize. However, other quadratic binary optimization models should be created and investigated as well, and the results compared. The model could be used at micro and macro scales after validation with real data and refining the disease evolution parameters. Thus, it could be used to evaluate lockdown schedules for university campuses and other large institutions with housing, example, military bases, and with more refinement could be used for cities and neighborhoods. It should be noted the model cannot be used as a one-time exercise, but due to the many variables and chaotic behavior of the disease, one should constantly reevaluate the model at each evolution, tweak the parameters, and do the optimization. As vaccines become available, the model can be modified and even used to predict a more optimal vaccination schedule. I would like to thank the team that has put together this presentation and the researchers that have worked on the code and producing these results. You can see the team members on the next slide. And after that, there will be a few slides which are the appendix that you can pause and get more details of our model. I will return on the last slide. We acknowledge the following contributions that made this research possible. More details can be found at the links below. We would like to thank D-Wave Systems for making their quantum and hybrid resources available to us and the COVID research community to encourage this important research. By the time of the QUBO conference, we expect to have a manuscript of the research available as well. Finally, we would like to thank you for your time and interest. Please please feel free to connect with any of the team members on LinkedIn.